The expansion of the universe is a scientific fact we have accepted for nearly a century. It is far more than a simple line in a textbook, it is one of the most fundamental pillars of cosmology. However, behind this concise statement lies one of humanity's deepest insights into the cosmos, as well as one of the most baffling mysteries in modern science, the Hubble tension. The story is a long one, so let us explore it together. Before we begin, remember to like and share this content. Nearly 100 years ago, Edwin Hubble, a gifted American astronomer, discovered a startling phenomenon while studying the light from distant galaxies. He found that almost all galaxies are moving away from us, and the farther away a galaxy is, the faster it recedes. This is much like a loaf of raisin bread rising in an oven. The raisins move away from each other, and those spaced further apart separate at a higher speed. This discovery overturned the then prevalent view of a static universe and opened a new chapter in modern cosmology. This gave birth to Hubble's law, which describes the linear relationship between a galaxy's recession velocity and its distance. In simple terms, velocity equals the Hubble constant multiplied by distance. This proportional coefficient, the famous Hubble constant, is not just a number. It acts as a cosmic yardstick that determines the expansion rate of the universe, revealing its age, size, and ultimate fate. Understanding the Hubble constant is akin to mastering the pulse of the universe. It defines our basic understanding of the cosmos we inhabit. If we can precisely measure the rate of expansion, we can trace back the history of the universe to determine when it was born, and we can look forward to predicting whether it will expand forever or eventually stop and contract. Thus, the Hubble constant is a vital link connecting the past, present, and future of the cosmos. Yet, this foundational constant has plunged modern cosmologists into an unprecedented crisis. Different measurement methods have yielded starkly different values, leading to deep confusion. To understand the origins of this Hubble tension, we must first look at how scientists measure this expansion rate. One primary and long-standing method is known as the cosmic distance ladder. Imagine you want to measure the distance to a far-off mountain but lack a direct tool like a giant tape measure. You might first measure the distance to a nearby tree, then from that tree to a hill, and from the hill to a forest, building a system step by step until you can calculate the distance to the mountain. The cosmic distance ladder works on a similar principle. It begins with nearby objects whose distances can be measured with extreme precision and extends step by step into the deep universe using objects of known brightness, called standard candles. Every step is critical because errors in one stage accumulate in the next. The first rung of this ladder usually involves nearby stars measured through stellar parallax. This is the most direct and reliable method, similar to how human eyes perceive depth. As the Earth orbits the Sun, we observe nearby stars from different positions, causing their apparent location to shift slightly against the backdrop of distant stars. By measuring this parallax angle and knowing the size of Earth's orbit, we use simple trigonometry to calculate the distance. While precise, this method is limited to stars within a few thousand light-years. However, these direct measurements serve as the bedrock for calibrating further distances. When direct methods fail, we turn to Cepheid variables. These are massive stars whose brightness pulsates periodically. In the early 20th century, Henrietta Leavitt discovered that the pulsation period of a Cepheid variable is directly related to its intrinsic brightness. By observing the period, we can determine how bright the star actually is. By comparing this to how bright it appears in our sky, we can calculate its distance. Advanced instruments like the Hubble Space Telescope can observe these variables in galaxies tens of millions of light-years away, allowing us to calibrate even more distant indicators like Type 1a supernovae. Type 1a supernovae are the ultimate standard candles for reaching the deep universe. These occur when certain white dwarfs reach a critical mass and explode in a violent thermonuclear blast, briefly outshining entire galaxies. Remarkably, almost all such supernovae have a nearly identical peak brightness, making them universal standard bombs. Because they are so bright, they can be seen billions of light-years away. By correlating their recession speeds with their distances, scientists calculate a Hubble constant of approximately 73 km per second per megaparsec. This value represents the expansion rate of the local universe and forms one side of the great debate. To peer into the expansion rate of the early universe, scientists look to a different messenger, the cosmic microwave background radiation. This faint electromagnetic signal is a remnant of the Big Bang. In its infancy, the universe was a hot, dense plasma where photons were trapped by charged particles. As the universe expanded and cooled, about 380,000 years after the Big Bang, electrons and protons combined to form neutral hydrogen. This made the universe transparent, allowing photons to travel freely. Over billions of years, these photons were stretched into microwave wavelengths, creating a snapshot of the infant universe. This map contains tiny temperature fluctuations that represent the seeds of all cosmic structures like galaxies and clusters. The Planck satellite was launched to map this radiation with unprecedented precision. By analyzing these fluctuations through the lens of the standard cosmological model, known as the lambda cold dark matter model, scientists can derive the Hubble constant. This model assumes the universe is composed of 5% ordinary matter, 27% dark matter, and 68% dark energy. By fitting the Planck data to this framework, scientists calculate a Hubble constant of approximately 67 km per second per megaparsec. This creates a gap of about 10% compared to the local measurements of 73. This discrepancy is the heart of the Hubble tension. It is not a simple measurement error, the difference is statistically significant, suggesting the two methods are fundamentally irreconcilable within our current theoretical framework. This crisis suggests that the lambda cold dark matter model may be incomplete or that there is new physics yet to be discovered. It is like a puzzle where the last few pieces simply will not fit, implying we might be missing a key component or fundamentally misunderstanding the overall shape of the universe. This tension affects our estimation of the age of the universe, its density, and its final fate. If the Hubble constant is higher, the universe is younger; if lower, it is older. While this uncertainty may make the foundations of cosmology seem shaky, it is actually a primary driver of scientific progress. When existing theories cannot explain observations, it often signals the dawn of a new era of discovery, forcing us to rethink the very fabric of the cosmos. We are approaching an entirely new stage of discovery. Just as Newtonian mechanics failed to explain the orbital precession of Mercury, a small deviation that ultimately paved the way for Einstein's general relativity and revolutionized our understanding of gravity and space-time, the Hubble tension may play a similar role. It is pushing us toward a breakthrough in the fundamental theories of cosmology. This obstacle has forced scientists to explore two main paths. Either our standard cosmological model requires significant revision due to undiscovered new physics, or we must uncover hidden systematic errors within our current measurement methods. It is like a detective investigating a cold case; either the culprit is someone never suspected, or the interpretation of the existing evidence has been flawed all along. One hypothesis suggests that during the early stages of the universe, there may have been a form of early dark energy or other unknown particles. We know that dark energy drives the accelerated expansion of the universe today, but if it behaved differently in the infant universe or during the recombination era, it could have altered the expansion history. This would mean the Hubble constant derived from the cosmic microwave background is lower than the actual value because our model didn't account for this temporary boost in expansion. Another possibility involves dark matter. While we currently view it as cold and only interacting through gravity, it might possess complex non-gravitational interactions or exist in multiple species. Such complexities would change how matter clustered in the early universe, affecting the expansion rate in ways our current models cannot predict. Even neutrinos might hold the key. These nearly massless, ghostly particles are everywhere. If there are additional types, such as sterile neutrinos, or if their masses are larger than currently estimated, they would increase the energy density of the early universe. This shift would alter the signature of the cosmic microwave background and change our derived expansion rate. Furthermore, some bold theories suggest we should re-examine general relativity itself. While it has been incredibly successful, any slight deviation in how gravity behaves on a multi-billion light-year scale would require us to modify our description of cosmic expansion, potentially resolving the discrepancy in the Hubble constant. On the other hand, scientists are working tirelessly to identify potential systematic errors. In the cosmic distance ladder, the primary concern is the reliability of our standard candles. If the parallax measurements used to calibrate Cepheid variables have a hidden bias, or if the chemical composition of different galaxies affects the relationship between a star's period and its luminosity, the entire foundation of the ladder shifts. Similarly, while Type 1a supernovae are excellent tools, they are not perfect. Researchers are investigating whether internal differences between these explosions or the way cosmic dust obscures their light might be skewing the results. Even with the Planck satellite's precision, we must account for local variations. It is possible that we reside in a local void, a region of space that is relatively underdense, or are influenced by the gravitational pull of nearby large-scale structures, which could create a slight bias in our local measurements. To break this deadlock, scientists are developing independent third-party methods. One promising technique involves gravitational lensing time delays. When light from a distant quasar is bent by a massive foreground galaxy, it creates multiple images. Because the light paths differ in length, the signals arrive at Earth at different times. This delay is directly related to the Hubble constant, providing a way to measure expansion without the distance ladder. Another breakthrough method uses gravitational waves from neutron star mergers, known as standard sirens. Unlike light, the strength of a gravitational wave provides a direct distance to the source. If we can also detect the electromagnetic counterpart, like a gamma-ray burst, to identify the host galaxy, we can determine its recession speed. This provides a completely independent measurement of the universe's expansion. As we look to the future, we are entering a golden age of observation. The James Webb Space Telescope is the center of attention. With its massive mirror and infrared capabilities, it can peer through cosmic dust to observe Cepheids and supernovae with unprecedented clarity, refining every rung of the distance ladder. If Webb's data continues to support a higher Hubble constant, the case for new physics will become nearly undeniable. Meanwhile, the Euclid Space Telescope will map the large-scale structure of the universe in 3 dimensions to constrain the nature of dark energy, while ground-based observatories like the Simons Observatory will probe the cosmic microwave background with even greater sensitivity. Ultimately, next-generation gravitational wave detectors like LISA may become the ultimate weapon in resolving this crisis. By accumulating data from enough standard sirens, we can measure the Hubble constant with extreme precision, free from the biases of electromagnetic radiation. Whether these new results support the local measurements, the early universe theories, or reveal a third, completely unexpected value, the impact will be revolutionary. The Hubble tension is not a failure of science, but a ladder for progress. It forces us to re-examine our fundamental assumptions, drives the exploration of new physics, and accelerates technological innovation. It reminds us that our understanding of the cosmos is far from complete and that the universe still hides profound mysteries. Whether this puzzle is solved by a better ruler or a completely new branch of physics remains to be seen, but it will undoubtedly be the most fascinating story in cosmology for decades to come. That concludes our exploration for today. I hope this leaves you with a sense of wonder. May you have pleasant dreams and a wonderful day ahead. See you in the next episode.